Welcome to a session for Lab F, which is about thermodynamics. So we're going to come across the ideal gas law and the combined gas law, which is actually pretty much the same. And I'm going to do the second part here, or at least give you an introduction of that. First of all, I'm going to just copy all this long URL, internet location, and that's what we're going to work off. And then we're going to go through here first some definitions, isochoric, isobaric, and then increase, decrease, the kind of thing, adiabatic, add, remove, isothermal. Get a little bit familiar with that, so have that printed out as you do actually the exercise online. Mean square velocity you will come across. Is the average speed of the particles. I'll show you in just a moment. I would do here part A as an example, but I ask you to do part A yourself and then see if you can match my numbers that I have here. And then again, still read through it. I'm going to do part B as an example so that you can see I get a fresh start here. And what it says is decrease pressure and add heat, start, wait for it until it stops, which is about 45 seconds, record pressure, temperature, and volume, show your calculations using the combined gas law. That's the code, gas, obey the law. Okay, let's do it online. And I have already opened the website ahead of time. So I'm just going to scroll down. Here's the applet. And it says decrease pressure. So I'm going to change this one here to decrease pressure. And heat, I'm going to say add heat. Okay. And then I hit the start button. And what you see here is a chamber with a piston on top. And we have quite a few molecules in here that are moving around, and they're hitting on the pistons, and perhaps it expands, perhaps it stays constant. Now down here you can see that the mean square velocity has shown up. It increases. That means that they're getting faster, and it also means the temperature is higher. Just off the screen gets now the external pressure increase. Decreases, because that's what we said. Notice that the piston actually expands, so the volume gets larger, so we expect that as well. As I said, it takes about 45 seconds. And there are the numbers, and I'm going to write them down as pressure of the gas changed from 0.55 to 0.57. Temperature of the gas changed from 382 to 466. And of course, the first one is an atmosphere, so 0.55 atmospheres, and the second one here is in Kelvin, so 382 kelvins, which is just above the freezing, no, not just above the freezing point. It's 109 degrees Celsius, or 200 Fahrenheit, 340 Fahrenheit, in fact, changed and increased even more to 466 kelvins. And then the volume, that is in milliliters, 61.4, changed to 72.5. Okay, so these are the measurements here on what happened to the piston. So we're decreasing the pressure, we're adding heat. That means the volume had to increase, and that's what we saw. So now I'm going to go back to Word, and I'm going to write down those numbers. Okay, and from the previous example, I'm just going to copy this one here and then insert them right there and use the new numbers that we just got. So the numbers I got were 0.55 atmospheres, 61.4 milliliters, and 382 kelvins. Those were the original data. And then we end up with 0.57 atmospheres and 72.5 milliliters and 466 kelvins. So in the combined gas law, the ideal gas law, the parameters, the variables that can change are pressure, volume, and temperature. What possibly could change is the number of molecules, but you saw it was a closed chamber, so the same number of molecules were in there at all times. So in the number of moles was the same, and therefore it doesn't enter into the equation. Okay, anyway, that's where we're going to calculate on the graphing calculator. So I'm going to do 0.55 times 61.4 divided by 382. Let me go over there. Let's see, there it is. Okay. So 0.55 times 61.4 divided by 382. There we go. And the other side is 0.57 times 72.5 divided by 466, and that of course is what you also have to do. Now I'm going to write them down. On the left, 0.88403, and I guess then I better quit anyway. 0.088. 0.08868. I guess. So remember these numbers and plug them in. So what I have here is on the left-hand side, 0.08843, and that equals or doesn't equal the right-hand side, 0.088680. Put a question mark in here for just a moment. I have to look at the significant figures. Well, on the left-hand side, 0.55, that's 2. This one is 3. This one is 3. I have to use the smallest number of significant figures. So these 3 will have to go. I'll take them away in just a moment. On the right-hand side, same kind of deal, 2 significant figures. So these 3 have to go. Notice that at this point here, they're really close. Why they're still a little bit different? Well, they have to be different a little bit starting in the third decimal simply because it's not significant. We weren't that accurate. Had we been more accurate on the pressure, 0.5723 or what have you, then our result would be more accurate. But we have to cut these off. So this one here actually rounds to 0.089, and this one here rounds down to 0.88. Still, the two numbers are the same because within our measurement errors, we are that close that, sure, there can be a slight difference in the second significant figure here. In fact, there is. One of them rounded down, the other one rounded up, and between 88 and 89 we have a difference of 1%, which is definitely permissible given that we only have 2 significant figures. So that's what you would have to do, and what this equation here shows you is that the combined gas law is indeed correct. One last thing about this one here, to the mathematician or the uninitiated person, this looks really strange. We know those two numbers can't be the same, but they really are the same. They are the same within measurement errors. And I underline that, very important. Okay, and with that one, I finished this recording on LEP F to give you an idea of what you have to do there, and pretty much you have to do the same thing that I did here several times over.